a short Q&A at 6 o'clock. So do send in your questions until then. And we'll hopefully get to those around 6. And yeah, hi, Alex. Another Andrew in the house. Hi, Emma, James. So we're just going to give everyone the opportunity to kind of join in now, because some people might be running a bit late. But I read in your bio, Jamie, that you're also an aerospace engineer.
I am.
So what kind of, firstly, what made you choose aerospace, and then, of course, the space industry?
Oh, well, depends if you want a long story or a short story.
The 2-minute story.
2 minute, okay. Well, engineering. I mean, I've been into engineering since I was a kid. Really, it's the classic building model rockets when you're a toddler and stuff like that. So that's always been something, a passion of mine. And the space, I got into space kind of towards the end of secondary school, probably. I read the book The Universe in a Nutshell by Stephen Hawking. I don't know if you read it, but
I haven't, not yet, no.
It's a great book. I recommend it. It's more astrophysics than aerospace, I suppose. But that got me thinking about space and things relating to that. And then I kind of discovered aerospace engineering, and it was this perfect union of the two, I suppose. And just kind of got led down that path, and here I am. What about yourself?
Slightly similar. I was always like passionate about maths and physics, and then when I discovered that there's something called aerospace, or aeronautical, some people like to call it, it was, as you said, it was the perfect match for me as well. Like I loved physics, and for me it was a lot about just grasping the concepts of the universe, which inspired me to like choose the space industry. But definitely, I completely resonate with the fact that when you said the perfect kind of composition of all the different passions turned into aerospace engineering. Very similar story, actually. But yeah, that's kind of what led me. But what led you to reaction engines?
Well, so kind of on the same, when I discovered that aerospace kind of existed, I suppose, started having a Google around what companies actually kind of push the limits, I suppose, and what companies, in the space industry kind of doing new stuff and cutting edge stuff. And discovered reaction engines. I suppose this was back in 2012, maybe, something like that. And I mean, the work they were doing was just awesome, and I thought, this is really cool. And I kind of kept an eye on them throughout uni. So I did before uni, I did a year in industry. I worked at a composites firm up in Stevenage, just north of London, and then kind of kept in touch with kind of what reaction engines were doing, and went for a tour around the site, and then went through uni and kind of specialised more in kind of like the aerodynamics side of things and stability analysis at uni. But then saw that reaction engines had a grad scheme, and I was like, well, this is a dream come true. So I applied and got in, fortunately, and it's been great. Been 10 months now, and it's been really, really interesting work. Really, like you're constantly busy, and you're constantly stimulated by the work, which I think is really important. It's something that's quite unique to engineering, I think, because you always get a sort of interesting package of work. So here I am, I suppose.
That's awesome. That's a great story. Just a reminder to everyone joining us, we're going to be talking more later on at around 6 o'clock during our Q&A, but I'm going to let Jamie share his screen now, and he's going to talk you through a lovely presentation that he's put together. So keep your questions coming in, and I hope you guys enjoy the presentation. I'm going to hop off now and be back at around 6 o'clock.
Great, thanks, Laksh. I'll start showing my screen now, and let me know if you can't see it. Maybe let me know when you can see it, and I'll crack on.
Yeah, that's all good.
All good. Okay. Well,
hope you guys enjoy it.
Thanks, Laksh. So thank you all for coming, guys. This is new for me. So we live in pretty strange times at the moment with COVID and stuff. So doing stuff like this is it keeps things interesting, doesn't it? It keeps things exciting. So my name's Jamie Wakefield, and I'm currently a graduate on the graduate scheme at Reaction Engines. I joined about 10 months ago. For those of you who weren't here for the chat a minute ago. I'm currently on my first placement, which is the design engineering placement. So I've been working primarily on our Demonstrator engine, our Demonstrator core engine, I should say. I've been applying I've been working primarily on the regenerator subsystem. I'll talk about that a bit more in detail a bit later on. But I've also worked in our applied technologies department, and we've been, me and the team have been looking at miniaturizing our spiral heat exchange tech and applying it to motorsport applications, which has been really cool and something quite different. So a bit about background on myself. If you missed a bit earlier, I graduated from University of Bristol with a Master's in Aerospace Engineering last year, so July 2019, and I specialised more in kind of aerodynamics and stability analysis. But for anybody that wants to know that I'm not just an engineer, I'm a well-rounded person. I do enjoy baking a lot of bread in my spare time. And if you have any bread questions related to your lockdown bread problems or escapades, then let me know and we can chat about that too. But what does Reaction Engines do, I suppose, is the first question to answer. Well, we're founded on the principle of the Sabre engine. And this is the main drive for everything we're doing in the company. So our goal is to essentially revolutionize space access and access to hypersonic flight by providing the Sabre engine, which is essentially this hybrid between a rocket and a jet engine. And the goal behind this is to reduce costs surrounding kind of access to space and provide kind of airline-like operations and much higher reliability, because rockets are pretty dangerous as they stand. So all of this is enabled essentially by our spiral precore technology, and this is really the flagship, I suppose, of our heat exchanger tech. And over the years, we've realised that actually this heat exchanger tech can be applied kind of here and now whilst we develop Sabre. And this leads quite nicely into the three pillars of what we do. So Sabre is our main drive. And this is a new class of propulsion aiming to kind of revolutionize access to space, I suppose. But we also are looking into hypersonic flight and very fast supersonic flight using the Sabre engine and kind of derivatives of the Sabre engine. But the kind of here and now and what we're putting on the ground now, I suppose, is we're looking into using our heat exchanger tech for the motorsport industry, like I said, the energy industry as well, capturing waste heat from power plants to increase efficiency, as well as battery tech and other aerospace applications where we can reduce weight. And essentially, we have this uniquely powerful and lightweight heat exchanger. So wherever you need a heat exchanger, which is quite a lot of places, we can apply what we're doing. But the reason why most of you are probably here is the Sabre engine. So I'll start from the basics. So rockets, you carry all of your fuel and you carry all of your oxygen. All the way, and you burn it in a combustion chamber, you chuck it out the back to produce your thrust, and you take that all the way up with you through the atmosphere into space, kind of dropping off bits of the rocket on the way to kind of frantically try and reduce the amount of weight you've got. But if you think about it, we've got a whole atmosphere full of oxygen that we can make use of up until we reach that point of exiting the atmosphere. So why can't we use this? Well, this is what Reaction Engines is trying to do. We've designed an engine that can actually operate as a hybrid, and it can operate in air breathing mode and rocket mode. So essentially from standstill to Mach 5, which is 5 times the speed of sound, it can operate as an air breathing engine, kind of similar to a jet engine, but one with a rocket on the back. And then from Mach 5 to Mach 25, which is 25 times the speed of sound, it can operate in rocket mode, and that front nacelle there closes up, and that gives you a final boost into orbit that you need. but I suppose then the main benefit of this is that you haven't got to carry all of that liquid oxygen, and you've got to carry much less fuel with you into orbit. And so what you can do is essentially open up the ability for looking into single stage to orbit spacecraft and or two stage to orbit spacecraft, stuff that you can't do with current technology. So this is fantastic, right? But why hasn't it been done already? And the main problem with being able to do something like this is the heat. So essentially, so say we're traveling at Mach 5, right? We're pretty high up in the atmosphere. The air's cold, but the problem is when we start to decelerate that air into the engine and compress it, so as it decelerates, it compresses, it heats up, because all of that kinetic energy and the speed of the air is getting transformed into heat energy, thermal energy. And how it turns out is that at Mach 5, you actually end up seeing temperatures of about 1,000 degrees centigrade at all points along the skin and in the engine. And that is far too hot for engines to deal with. You're talking way above the melting point of things like aluminium alloys. And that's before you even start doing anything with it. So, you want to be able to put this into a compressor, compress it, and then put it into a combustion chamber to burn it. By that point, you'd be talking, a couple of 1,000 degrees centigrade. So what we've got to do is we've got to cool down this air before it gets to our engine. So this is the kind of major technological breakthrough. And what we need to do, and what we do with our precooler, is we cool down this 1,000 degrees centigrade air down to, I think, minus 150 degrees C in about a 20th of a second. And to put that into perspective, that's about twice as fast, as it takes for a human to blink your eye, basically. So these are pretty incredible numbers and pretty cool stuff. And now, once we've got this cool, dense air from our precooler, we can actually use it in a kind of almost a traditional jet engine cycle. So we can take our cool, dense air, compress it, stick it in our combustion chamber, and burn it with our hydrogen to produce our thrust. But waste not, want not, we've also got a huge amount of heat that we've extracted from that air, and we can do stuff with this, yeah? So we've got a helium loop running through our precooler, which extracts heat from the air, that kind of, 1,000 degrees C air. And we use this helium, hot helium, to drive our turbo machinery in the core engine itself. And we've got enough heat left over in that helium to actually re-inject heat back into the cryogenic hydrogen and boost the amount of thrust we can get out of it, which is pretty cool. So this kind of regeneration of the waste heat, if you will, has been a big part of what I've been working on as a design engineer at Reaction Engines. So yeah, again, this precooler is what makes it possible. It's ultra lightweight, ready for flight, incredible performance, and the numbers are staggering. So I said about cooling it down from 1,000 to minus 150, twice as fast as you can blink an eye. But the full size version of this precooler, so the one that you can see in this image here, that kicks out, a heat transfer power, if you will, of 400 megawatts. Might be quite a hard number to put your finger on, but essentially that is enough power to power a small town, over 200,000 houses, which is pretty incredible. Or you could say it's the same power output as about 150, I believe, onshore wind turbines, which is crazy numbers. And it's all down to precision engineering, essentially. So this spiral precooler is constructed from tens of thousands of microtubes wound in spirals. And each one of these microtubes, if you kind of look at it end on, you can see, if you looked at the wall of that tube, the wall thickness on that tube is less than the width of a human hair. So when you look at these things end on, you can barely see the wall of them if you've got a straight enough tube. And it's pretty amazing tech. So kind of taking a step back, I suppose, this is just some of the few big milestones we've hit as a company throughout the years, throughout the last 5 years, I should say. And I suppose one of the big takeaways from this is actually we've been growing kind of exponentially as a company over the past 5 years. So I think it was something like 15 years ago, we were about 9 people, to 5 years ago, we're about 50 people. And today, I think we're just over about 200. So it really is accelerating, growing exponentially. And it's a really exciting time to be working here. I won't go through each one of these, we'll use up too much time, but the real big, icing on the cake was this 2019 HTX testing. So that was when we tested our precooler to Mach 5 conditions, and it was spoilers, but it was a great success. And essentially it proved out our heat exchanger tech, which was the make or break point for our Sabre engine. I'll go into a bit more detail on that towards the end of the presentation, actually. But for now, on the topic of our growing workforce, I suppose it's worth pointing out that we pride ourselves on being a really diverse team, and everybody brings a myriad of kind of different perspectives and experiences into the company. We've got quite a young average age actually at the company, so I can't remember what it is, but it's pretty young, and it's far from the kind of stereotypical stuffy engineering company you might imagine when you're choosing a career when you're younger. Got some really progressive minds doing some incredible work. And we've made a huge amount of investment into our kind of manufacturing base in Oxfordshire as well. So because our precooler tech is so important and so critical to what we do, we control every aspect of it. So, we can, from a conceptual design to a detailed design to the manufacture of it, which you can see that we have this custom vacuum brazing furnace on site in Oxfordshire, and that's a precooler, part of a precooler being on the bed there. And then we also we can also inspect these things and test them. It's every stage in the product life cycle, essentially. And downstairs from the offices, in kind of pre-COVID times, I suppose, we've got our precision machine shop just downstairs. So I can, as a design engineer, I can sketch stuff up, do a quick drawing, and run downstairs and chat to machinists to get their input onto whether it's machinable, whether tolerances are in check, stuff like that. It's really useful stuff, and we have a really cohesive kind of working environment like that. I suppose, like this Zoom call, Reaction Engines is global. So we've got our main headquarters in Culham in Oxfordshire, and this is a really cool place to work actually, because we're on the in Culham Science Centre, just outside Abingdon, and just next door to us is the UK Atomic Energy Authority. These are the guys that are world leaders in fusion power. So you've literally got the leaders in fusion power next to reaction engines, unlocking kind of space access and hypersonic flight. It's a really cool place to work. But we've also got this base in Colorado now, which is relatively recent, and that was actually where our precooler testing was carried out. So the guys out there are doing some great work, basically. So a bit of a deeper dive for, I suppose, the tech heads out there who just want to know how does Sabre work. And I totally get that, because it's exactly what draws everybody to reaction engines. It's what we do. So essentially, we're traveling at Mach 5, say, we've got cold air outside. But what happens is, as this gets drawn through the intake, it goes through a series of shock waves. And as it goes through these shock waves, the shock waves compress it, slow it down. So in here, it's subsonic and it's very hot, as you remember. So we take this subsonic hot air and it gets drawn through our precooler, cools down to -150, something like that. And when it gets into the core of that precooler, we've got cool, dense air. We take that into the core engine, compress it further through a turbo compressor system, and then pump it into the combustion chamber. But simultaneously, we get the kind of extracted heat from that helium loop, driving the turbo machinery, and re-injecting heat back into the hydrogen, so that we can improve the efficiency of the burning in the combustion chamber. And the key advantage of this kind of this design, I suppose, the design of this engine, is that we can actually separate out each part of the engine into separate modules. So we've got the kind of intake here, that's kind of one bit, and then you've got the precooler, that's another bit, and then the core engine, and then the nozzle and combustion chamber. And so essentially what this means is that when we're testing Sabre, we don't have to just build the whole of the Sabre engine, chuck it on a plane, cross our fingers and hope for the best in a flight test. We can actually break it down into chunks, manageable chunks, ground test each system independently, and then do integrated tests later on. So, you know, out of this, we've tested a precooler. We've done a pretty substantial amount of work into the nozzles design as well, and we're currently testing the core engine with our demonstrator program, which I'll chat about again in a minute. But the key takeaway is that we've designed an engine that can go from standstill, from 0 to Mach 25, with the ability to use both atmospheric air and onboard oxygen. So it's an all-in-one solution, and this means that we've got this unique operating window and a real kind of gap in the market that we can fill. So these are some great graphs actually. If you like graphs like me, the top graph shows the efficiency essentially. So as the numbers increase on that y-axis, that's getting more efficient, and then you've got a Mach number on the base there. And essentially rockets, right? These are the only way we have to get into orbit at the moment. And people are doing some great work with rockets, don't get me wrong. You know, SpaceX is doing great things, all the others as well. But they are fundamentally, they're pretty inefficient, to say the least. And the difference between a rocket here and the Sabre engine in terms of efficiency is pretty staggering. And it's only actually once we get up to, you know, just above Mach 5 that we need to transition to rocket mode, and the efficiency drops back down to rocket levels. But we've got this whole area here where we can, like, we're benefiting from this huge efficiency boost, and that drop down to, you know, to rocket efficiencies combined with this step up in thrust to weight ratio that can give us that final boost into orbit. So it's pretty kind of market changing stuff, and this is the kind of the goal, I suppose. So this is what we can enable. So the keen-eyed among you will notice that these numbers might be slightly out of date. So the current status was, you know, 150 million per rocket launch, and SpaceX is doing some incredible work, and they've been driving down this kind of partially reusable route, and they've driven this down, I think, to about 57 million. Last night I checked, per Falcon 9 launch. So they are creeping ever closer to us, but I mean, the difference is still staggering. I mean, 15 million versus 62, it's a big jump, and still a real game changer in terms of cost. But it's not all about cost either. We're talking about a launch system that can not only beat the others in terms of cost, but responsiveness. We're talking about turnaround times around 2 days. And what that means is we're getting close to kind of airline-like operations and just ultra-fast on-demand space access, essentially. And a kind of a side effect of reusability, I guess you could say, is that the reliability is far anticipated to be far better than rockets. And rockets are really quite dangerous things to fly in. I don't know if I'd ever fly on one. Probably would still, but anyway. But they are dangerous, and we can really improve on how reliable they are and how safe they are. And I suppose on the topic of that, you know, the work that SpaceX is doing, all the work we're doing, all the work SpaceX is doing is really making the industry really much more healthy. Like, competition is exactly what the space industry needs, and you know, up until very recently, it's been really stagnant. Well, not stagnant, but in terms of launch vehicles, like, you know, it's been pretty stagnant in terms of it's only accessible to big governments with huge space budgets. And the work we're doing and the work that obviously others are doing as well is bringing kind of it's a build it and they will come approach, essentially. So private entities are now thinking, oh, hold on a minute, we can get stuff into space, we can get satellites into orbit. And the keen-eyed among you will notice actually that I've been talking about single stage to orbit, and this shows a two-stage to orbit. And this is a real highlight of the kind of versatility of the Sabre engine. So we can actually use two-stage to orbit as a sort of stepping stone on our way to single-stage to orbit. And another advantage of this versatility is we can actually start looking at Sabre engines and Sabre derivatives in supersonic and hypersonic applications. And this is something we're actively pursuing and is a really exciting territory. I mean, we're talking about, Concorde 2.0, but 3 times as fast. So it's really cool stuff. And what we can provide here is an engine that can go from standstill to Mach 5. And essentially, unless you've got a rocket, not much else can do that. You've got ramjets and scramjets, which are great and can take you really fast, but they don't work below in subsonic speeds. So you're talking like you've got to boost them up to Mach, I don't know, 1.5, something like that. 1.5 times the speed of sound before they even start producing thrust. And getting them there, when you start thinking about, okay, I want a hypersonic commercial airliner powered by a ramjet, you start to question, well, how am I going to get it up to Mach 1.5? I've got to strap it to some other much bigger aircraft that can go up to Mach 1.5, and it starts getting complex and very, very kind of undesirable almost. And what Sabre can give you is something that's 0 to 5 the whole way. And as you can see, it's a real growing market. I mean, loads of people and governments are really interested in getting hypersonic technology, getting it going. And an advantage of hypersonics for reaction engines is that we can actually do this work, in parallel with the development of Sabre. And in doing this, we kind of get our technology flying and out there while we're developing Sabre, and feed the learning from that back into Sabre, which is some really interesting stuff. And this is again just showing how do we fit in. We've got this 0 to Mach 5 engine, and just nothing else matches this. So the Blackbird, the SR-71, that goes up to Mach 3-ish, I believe. But you can't get any faster than that, because then you just get heat problems. And I believe even the SR-71, it can't take off on a full fuel load. You've got to take off on like half load or whatever, and then get an air tanker to fill you up. So we've got a real opportunity here to make a big difference in the hypersonic market, which I think is pretty cool. So I guess the question is, why isn't this happening already? And the reason is, the faster you go, the hotter you get, as we discussed. And we've kind of settled on Mach 5 as the ideal, because anything above this is a law of diminishing returns. So to put this into perspective, right? So if you're talking about a commercial airliner today, you're traveling at, say, I don't know, Mach 8, Mach 0.8, Mach 0.9, something like that. You're subsonic, and it will take you at least 7 hours to get from London to New York, okay? Something Sabre powered that can go Mach 5 across the Atlantic could do it in about 90 minutes, which is pretty staggering, right? And the world isn't big enough to need anything faster than Mach 5. So there you go. So I guess back to kind of the here and now, this is, we've got this incredible heat exchanger tech that's been proven, and we can use this. And that's exactly what our applied technologies department's doing. So we've got all this in-house expertise with, bespoke modeling, designing, making and testing these things. And the question is, what can we do? And you've got to excuse my pun, limit. And we can really do a whole lot of stuff, a whole lot of really cool, interesting stuff. So personally, I've worked quite a bit on the automotive side. So we do miniaturizing. Imagine miniaturizing this behemoth into something much more compact, much more lightweight, but still really high performance, and applying this to motorsport applications, which has been really interesting work. But that's not the limit. You know, we've been applying this to extracting waste heat from power plants to improve their efficiency. So essentially, in a power plant, you know, you're venting how much heat into the atmosphere, which is just lost energy. And what we've done is we've actually put one of our heat exchangers kind of in this. Of course, I suppose it was I don't know, but to capture, we got our heat exchangers capturing this waste heat essentially, and converting this back into electricity and re-injecting it into the grid, and in that sense, making things much more efficient. Which is one of the first steps toward a greener future, I suppose. And we've also been looking at kind of aerospace applications, but not the hypersonic I was talking about earlier, but the kind of the here and now of using our heat exchangers in airliners, in kind of reducing weight. And as most of you will know, weight reduction in aircraft is the #1 thing you can do, and it dramatically improves fuel efficiency. So hopefully, once we're all flying again, we can make use of that. So I guess this, so I mentioned previously that each stage can kind of be separated out on the Sabre engine and tested kind of in chunks on the ground. But a real big plus, a real big positive, lost my track here. Oh no. So I guess the thing from first glance, you might not realize, like, you might look at the Sabre engine and think this is a hugely complex behemoth of high-tech machinery. But upon closer inspection, there's actually a huge amount of the tech in this engine is tried and tested tech. So turbo machinery has been done, rocket engines have been done, ramjets have been done, and intakes have been done. The big kind of can we do it or not was the precooler. And as you can imagine, testing that precooler and making sure that actually what we can make matches our models has been a really big priority for reaction engines. So this segues quite nicely into our successful test campaign. And it showed last year that our precooler can indeed survive cooling 1,000 degrees centigrade air down to ambient temperatures. And we tested our precooler in the US. So the question was, it was quite an interesting test campaign, because the question was, how do we actually get hot, fast air into our precooler? Because supersonic wind tunnels, I mean, they're behemoths. You don't want to deal with them. So what can we do? And quite a few years previously, we tested a precooler in slightly different conditions. So we instead put it on the front of a jet engine, essentially, in front of a jet engine, I should say, and let the fan of the jet engine draw air through the precooler to deliver kind of pre-cooled air to the jet engine. And this essentially tested precooler from ambient, room temperature to below minus 100 degrees centigrade. And this kind of proved out our frost control technology, because essentially once you cool down air, you end up condensing the water vapor that's in the air and then freezing that on your components, which is very heavy. And as a friend at work likes to say, we don't want to make the world's fastest and most expensive flying ice cube. So that tests our frost control tech on the front of an engine. So we thought, well, why don't we stick the precooler on the back of an engine and turn the afterburner on and just chuck the flames down it, and get it as hot as we can. And that's exactly what we did. So up here, kind of past the wall, we had an engine delivering with an afterburner on, delivering hot air to our precooler. And our precooler sat just here, so the air went radially down and then cool air out. And everything went really well. And the performance of this matched really closely to what we modeled in our predictions. It's pretty amazing to think that, if we neglected kind of how fast this air was moving, I definitely don't recommend you try this at home. But if you kind of imagine you could stick your head up just behind this precooler here and look straight through the core of it and see this glowing red hot afterburner of a jet engine, and feel a nice ambient breeze on your face. I think that's pretty cool. Obviously, it'd be quite a strong ambient breeze, but you know. So with the precooler testing completed, we're now focusing on testing the core engine part of Sabre, essentially, which is what this shows here. And this is our demonstrator engine. So what this does is it's going to prove the thermodynamic cycle of the Sabre engine. So what I talked about earlier regarding the closed helium loop, being able to power all the turbo machinery and re-inject heat back into the hydrogen loop, that's essentially what this core engine demonstrator is going to be proving. So it also tests all the kind of subsystems, Mach engine core, you know, pre-burners, turbo machinery, and my kind of love, I suppose, is the regenerator subsystem. So the regenerator heat exchanger takes your hot helium and your cold hydrogen and warms up the hydrogen, essentially. Sounds quite simple, but because we're great at heat exchangers, we have developed another really high-tech architecture of heat exchanger. So instead of using microtubes like the precooler heat exchanger uses, this regenerator actually uses microchannels. And there are some also crazy numbers associated with this. So you've got to imagine something the size of, say, a shoebox, right? And in this shoebox, this solid shoebox, there are millions upon millions of microchannels. And each channel has helium and hydrogen kind of flowing through it, heat exchanging and whatnot. But each channel is only slightly wider than the width of a human hair. And they are absolutely like tiny little things, and millions upon millions of them. So this demonstrator, this is being built as we speak. I mean, components for this are being built as we speak, and testing is going to start at the end of this year. So it's all coming together for the company, and it's all, well, it's a really exciting time to be a part of reaction engines. Everything's going really fast. And so the question we always get asked, this is the classic, when will we see Sabre flying? So it's a question we really want to answer, and we'd love to put a firm date on it. But it would be disingenuous. And because everything relies so sequentially on the thing that comes before it, as well as kind of funding rounds and stuff like that, all we can do is kind of take each step as it comes. But things are really accelerating, and each step along this path is kind of much closer than the last one was. So we've done our heat exchange test, and that was the make or break, and that went successfully. So now we're on to our kind of core engine test. And then you can kind of start seeing how kind of incremental each technology leap is after that. Like once we've done that, the integrated test is just putting them two together, right? And then flight test is putting on an aircraft, and hypersonic and space applications is getting it flying. So it's a really exciting time, and it is really it's going pretty fast. So hardware's being built and tests are being done, and we're making good progress. So all this is possible because we have a group of world-leading industry partners and government agencies backing us. And these guys, they all believe in our vision just like we do, and they're all really in the loop with what we do. So a really good team of agencies to work with. I'll be honest, this slide is some legal jargon. I don't entirely know what it means, but I suppose I should leave that for a second. That's probably long enough. Thank you very much for listening. I'll be really happy to take any of your questions now. Laksh, I don't know if you're still around or if I've lost connection halfway through or something.
No, I'm back.
Oh, good.
I was listening very carefully. No, that was great. What an incredible presentation. Thank you so much.
No problem at all. No problem.
I'm
happy to do it.
I'm glad you broke down some really, really complex ideas into some very simple language, which I really liked.
Oh, good. Oh, I'm glad. That's good to hear. It means I'm better at presentations than I think I am.
No, you're great.
I'll leave that up like that, shall I? And then we can flick between slides and stuff. I hope nobody minds.
Maybe make it full screen.
My notes. Yeah. Oh, it's a good test of my ability, isn't it? Slideshow. Individual. Let's try this. From the beginning. You see that?
Yeah, that's great.
Cool, I'll do. Right.
Awesome. We've actually had a couple of questions in already from Manus. And he is asking, or she, sorry, any thoughts of 3D printing all of the engine with appropriate materials? And have you guys thought about the use of graphene in the use of the engine and the aircraft eventually?
Graphene's an interesting one. I mean, I can't say, I haven't been obviously here for a huge amount of time. I can't imagine we'd be using graphene in the engine. Kind of, we're trying to stick to kind of tried and tested materials. So a lot of the stuff we're using, actually, I'll tell you what, I'll skip to the engine slide, because this is quite a key part of it. It's actually the because we're cooling down this air so much, we can use really lightweight kind of classic aerospace alloys in the engine. So we don't have to rely on really high tech, kind of high temperature alloys here. We can use pretty lightweight stuff. And along, all the kind of outside materials, we've been looking a lot at ceramic composites. So we've had a partnership with the NCC that got announced, I think, relatively recently, looking into ceramic composites. So that's what we're looking at there. And the first question was 3D printing, wasn't it? So 3D printing is really interesting. And actually, I'm sure we're probably thinking about 3D printing a significant amount of components, or what, I mean, I'm sure we're considering it for sure. I know that a lot of aerospace companies are doing similar things. So I think there's a company in the UK that are 3D printing rocket engines and ALM stuff. So yeah, I'm not that close to it, unfortunately, but we've got our CTO, Richard Barber, one of the founders, he does a lot of that sort of level of thinking. So yeah, hopefully, because it'd be pretty cool.
Definitely. I hope that answers your question, Manusus. I hope I said your name right. A question from Andrew Curtis, and he's like, "Hi Jamie, thank you for the presentation. I was wondering why the air breathing mode is limited to Mach 5.
Well, above Mach 5, everything just gets so hot. There's a few, I guess there's a couple of reasons. So the first is heat, I suppose. So you want to be dealing with, I mean, 1,000 degrees is hot, right? And we want to be dealing with temperatures that our precooler can withstand, I suppose. And the other thing is, actually, once we're at Mach 5, we're at pretty high altitude. We're kind of we're quickly running out of air, and we just need that increase in thrust to weight ratio to get us into orbit. And we've done the work of the air breathing engine, kind of when we're in the atmosphere, of, increasing our efficiency and whatnot. So at that point, we can just switch to a liquid oxygen source on board, have a quick boost of thrust, close up that nacelle at the front there, and just kind of fire off into orbit, I suppose. So I'd say that's probably the reason. Yeah, a couple of reasons.
To answer your question, Andrew. Another anonymous attendee. Thank you for this nice presentation. Do you think the heat exchanger developed by reaction engines can be integrated into next generation turbofans?
I'm sure it could. Yeah, I mean, everywhere, anywhere you need a heat exchanger, it does the job. So yeah, I probably can't comment on it much more than that, because I haven't been involved in kind of the aerospace side of that applied technologies thing. We've been doing more motorsport stuff, but yeah, I mean, it's possible, absolutely.
Yeah, I'm sure, why not? I hope that answers your question. Just gonna get rid of these. Ian Hill is asking, could this thermodynamic engine cycle work with other cold fuels like liquid methane?
Yeah, no, I believe so. So I think the hypersonic stuff is looking at using alternative fuels, hydrocarbon ones for that, as opposed to liquid hydrogen. So yeah, no, I believe so. Yeah.
I think we definitely have a scientific community in tonight watching this talk.
Yeah, technical questions. These are the good ones, to be fair, although I can't answer some of them.
I hope that answers your question, Ian. James Smith, another great presentation and very informative. A couple of questions here. What step, and it's one of the things that I was actually thinking as well, is what steps did you take from undergraduate study to be recognized and employed by reaction engines? That's the first one.
Okay. What steps did I take? Well, I'd say, you want to be, I think industry experience is quite a key thing at the moment. So getting kind of experience in relevant industries, or even just kind of, relevant experience in general is quite, it's really helpful because it gives you not only stuff to kind of talk about in your CV, but in interviews as well, you can relate what they're talking to you about to kind of real world engineering that you've done. And that, for me personally, that's really helped me having industry experience. Other steps, I mean, apart from, the classic work hard, I think enthusiasm, I suppose, just like having enough enthusiasm for the subject. Reaction engines is kind of built on enthusiasm, so I think that's been a big part of getting me here. Yeah.
Awesome. And then follow-on question to that is, what advice do you give to an aerospace engineering student? I'm sure we have a few aerospace engineers in tonight looking to follow in your footsteps.
Oh.
What advice would you give them?
Wow. Gosh. What advice do I get? I'd say, if you've got the it depends what year of aerospace engineering you're in, I suppose. But if you're in your first year or your second year, definitely look into getting some industry experience. I think that's really useful. It's by no means a necessity. I'm sure you could get a job without industry experience. I'm sure you can. But I think from a personal development point of view, it's just really useful thing to have behind you, so that it helps you choose what you want to do for a career as well. Steps as an aerospace student, I suppose, just concentrate, get the basics down, the foundations, because that's really important. So getting your kind of I think what makes a really good engineer a lot of the time is having a really broad understanding and knowledge of kind of all the different disciplines of engineering. So your stress and your aerodynamics and all the rest, materials and all of that. It's all really important, and a lot of what we do is bringing these things together in like systems engineering. So I think having a good kind of base in all of those and then specializing is like quite a good way to go about things. Gives you kind of a broader, a more well-rounded kind of engineer, I suppose. Makes you a more well-rounded engineer.
Yeah. Great. Just to go back on that, actually. So I had this question. I always had this question for people in the industry: is it's kind of like the chicken and the egg situation. Is you're not going to get a job if you don't have the experience, but you can't get experience if you haven't had a previous job. So how do undergraduates or people who are in any kind of engineering discipline, or even if they're interested in the space industry as a whole, because I'm sure you have people at Reaction Engines who are not engineers, of course.
No, so that's a really good point. So we absolutely have people that aren't engineers. So I mean, we've got people that have come from physics backgrounds. We've got an astrophysicist. We've got material scientists. We've got a whole range, basically. A whole range of people working here. And I guess the other point is that actually, doing a degree and a couple of years of work experience isn't always the route. Like it might be that like you want to go in through kind of an apprentice route or something like that, and we're really supportive of doing things like that. And we've got some really really talented people like working in as apprentices in reaction engines. So the chicken and the egg thing, I totally get that, because when you're applying for jobs kind of and applying for industry experience, it can be really demoralizing. And you can just think, well, how, they're asking for X amount of experience, but like I'm an undergraduate, how on earth could I have had that experience when I've literally, I've just come out of I'm still in education. And I think the thing there is just persistence, really. I think like it's just getting your it's just getting your foot on the ladder almost. It's just that little first step. and that first step gets you to the second step, and yeah, just kind of keep at it, and go for kind of experience roles that will help you build your experience, and yeah, just persist, I think. But yeah, stay strong. It's, yeah.
One thing I'd add to that definitely is I only recently also completed my aerospace degree, and for any students who are in the final years of their degree right now, yeah, as Jamie kind of resonate this at the start of our talk this evening, that is really to look what's happening in the industry you're involved in. You said you were looking at Reaction Engine's website in 2012.
Yeah,
you were looking at what they're doing, and it's really researching about the different companies, the different industries, that's kind of developing new things that you're interested in. Really researching, like follow their Instagram page, read what they're posting on their LinkedIn profile, so you're up to date. Because when it comes to like the all important interview, if you've been involved on their journey, even though you're not there, you'll know what to say, and that will show that you're committed to them. And I hope you are. Yeah, no, do your research.
Yeah, no, absolutely. I think that's showing that you've actually put the research in, especially when you get to an interview stage, is completely. I mean, it's what you need to show.
Exactly.
I think from kind of having looked at applications in the past, it's really you might, I guess, when you're doing applications, you might want to just fire off kind of a million applications at once and kind of do the copy and paste classic and just send them all off. But it's really not the way to do it. It's much better to really hone in and focus on like where you want to work, and just spend as much time as you can afford to just really tailoring your application, doing research. You know, company value is always a good one to look up. Make sure that you kind of know what the company wants in an employee, and see how you can. It's kind of imagining yourself in the company, and kind of talking about how you can contribute to what they're doing. And yeah, you can only do that really through a real good amount of research, I suppose.
Yeah,
definitely. Yeah, absolutely.
Well, I hope that answers your question, James, and all the other engineering students out there. Moving on to the next question from Matthew. And the question is, do you think the work you're doing is similar to other engineering graduates in major aerospace companies, for example, BAE, Rolls-Royce, and that the only difference is the innovation behind the product systems you're working on? I mean, I'd beg to differ and say that I'm sure BAE and Rolls-Royce are definitely doing some new development work and looking at innovative projects. But how would you say? I mean, of course, Reaction is very, very new compared to BAE or the others. How would you say that's different?
Yeah, I mean, these are great questions, by the way. I mean, really high quality questions. Yeah, so I get where you're coming from. I think BAE and Rolls-Royce and Airbus, they look like these huge behemoths, and they are really big companies, don't get me wrong, but they are doing like some really important like R&D work and development work. I suppose the unique part of Reaction Engines is actually that our whole company is focused on that, I suppose. So we're much smaller, so it's much more intimate. And I suppose it's kind of a day-to-day difference. I suppose we probably get chucked in at the deep end a bit more in terms of like the work you do, like civil work.
As a graduate, you mean in your day-to-day job?
Yeah. So as a graduate, I think on a graduate scheme in a different company, it might be that I don't want to say you kind of don't do. I think Reaction Engines is like it's so kind of I suppose pressing that it's like as a graduate you are instantly utilized, and and I mean that can be good and bad, because sometimes the massive support network that the company offers is really useful, but from a kind of learning on a job standpoint, I suppose that's a real advantage, is you get stuck in from day one. I suppose that'd be the big difference between what I do compared to kind of other graduates. But I mean, as you said, Laksh, like in every aerospace company, there is a huge amount of innovation, and
Yeah.
yeah, and that's only getting, that's more of a case as time goes on, especially now that people are looking into, the first net carbon transatlantic flight. There's big pushes for innovation in these companies. So yeah.
Yeah, no, great. That's such a great question, Matthew. Thanks for that.
Really good.
Moving on to Lawrence's question, and it's a simple one. What's the approximate length of the precooler that was tested? And do you know?
Oh, I don't know, I'm afraid. I'd be lying if I said a number, so I won't say anything. But yeah,
Well,
sorry. Good question, but I don't know.
is the length realistic? Is the length that was used realistic for integration into a full engine? I hope so. I mean,
yeah, I mean, well, it's big. I mean, the thing is big. If that's the answer you want, that's right. Like, it was a big thing.
yeah.
And it's definitely realistic. Is it the same size as a full size precooler on Sabre? It's probably a bit smaller, but it's representative for sure. Yeah.
Awesome. Yeah. So I'm sure Reaction Engine have got their dimensions.
Oh yeah. No, I hope so.
The micromillimeter.
Yeah. Yeah, we're big on the microns at Reaction Engines.
Awesome. Another question from Andrew. Thanks for the presentation. Is the plan to move the intake cone in subsonic air, so the air breathing mode, to control shock structure in a similar way to the SR-71? And is this work completed or ongoing?
Oh, well, I have no idea. I think I imagine that probably is the plan, because I know that we've got kind of similar kind of moving parts on our nozzle. I think there's a patent filed a while back now, but yeah, I mean the nacelle, the intake, the spike itself actually it moves forwards to completely close up the intake during rocket mode. So I imagine that it would control the shock structure like the Blackbird does. Yeah.
Awesome. Cool. So just a reminder to everyone joining us, we do usually end these at 6:30, but since we're having so much fun with Jamie and we've still got a load of questions to go through, we are going to extend tonight's talk. So stay tuned in, and we're going to move on to the next question by Aaron. Hello, Jamie. I have a question. We live in the hypersonic airplanes era, and you have a lot of competition. What are the advantages of your engine to be able to compete with the Lockheed Martin X-58 aircraft, for example? Gracias.
Well, so I mean, I guess for uniqueness, so I'll go back to that slide on the where was it? This one.
Showing the evidence now.
Evidence. Here you go. So this is, I mean, we're talking about something that can go from 0 to Mach 5 in a single engine solution, and I'm not aware of any other engine that can do that in development. And correct me if I'm wrong, Laksh, but because a high-speed jet engine, if it wants to get from 0 to Mach 5, it's going to have to look, I think, reasonably similar to a Sabre engine, to be honest. And if you're dealing with something like a ramjet or a scramjet, you need to get these supersonic before they can actually start producing thrust. So you need something essentially for them to piggyback on before they can actually start producing thrust and getting underway. So obviously for like hypersonic, if you're talking about like a hypersonic commercial airliner, for instance, yeah, the idea of kind of piggybacking on a massive like 747 that can go up to Mach 1.5, it gets pretty complex and pretty scary. So something like a Sabre engine, because it's such an integrated solution, an all-in-one solution, that's kind of the advantage it brings, is the fact that you can go from 0 to Mach 5 with relative ease.
Yeah. Awesome. Hope that answers your question, Aaron. Let's see. Sorry, just a bit of a jump around of questions on my screen as new ones are coming in.
Oh,
wow. Andrew just said, thank you for answering my previous question. And he's asking, how does the engine switch between air breathing and rocket mode?
Oh, yeah. So I think I touched on that a second ago, actually. So what happens is this this intake. Can you see my cursor on the screen, by the way?
Yeah.
Is that moving around for you? Or is that Okay, cool. So this cool. So this spike, essentially when this moves forwards through the engine, it closes up around this intake here. So what happens is this spike moves forwards, this intake closes up, and then you're left with this kind of essentially just a rocket engine, and you switch from kind of using, it will be a transition, obviously, it's not going to be like a hard switch between the two, but you switch slowly to using a store of onboard liquid oxygen instead. And yeah, then you've got essentially what is a rocket engine, but albeit a slightly complicated rocket engine with a bit of added weight on it because of its core engine. But yeah, it's all, I mean, this core engine itself and the pre-core is all pretty lightweight because we're dealing with kind of lightweight aerospace alloys as opposed to you know, crazy, I don't know, high temperature stuff.
Yeah, I actually had a question. Why is your heat exchanger testing happening in Colorado?
That's a good question.
Not in Abingdon.
Well, yeah, I probably couldn't say really. I mean, it's you know, we've got funded. I think on our last slide, you know, we've got DARPA. Yeah, we've got DARPA as one of our funding partners, and I guess doing work in the US is helping us build relationships out there. So yeah, I mean, yeah, but it was quite a feat because we obviously built it all here and then shipped it over, and it was pretty intense the shipping process. But yeah, imagine that's why.
I've got an intense question coming up from Lawrence.
Oh.
How do you create sufficient mixing for the delta Q required with a radial heat exchanger, and how was this simulated with a static test when there are no shocks in the inlet?
Well, so it's a very technical question. I must admit, I haven't worked on the. Huh?
Do you know Lawrence?
I don't think so. But he's asking some great questions. So let me get back to the slide here. Yeah, so we're not the aim with our pre-core testing, our HTX testing, it wasn't to accurately recreate like a shock structure around the intake. So you'll remember that if we go back to, I'm really flicking through slides here. So essentially your shock structure is all pretty far forwards, right, in your engine. So it's all around your nacelle here. And by the time you get to your pre-cooler here, where it's expanded through this part, you've got subsonic air, which is hot. And essentially we've captured, you can't see my hand, but I was going like this. We've captured, we've kind of cut it off here and captured that part of it. So essentially we don't need to have supersonic air going through here. We've just got really hot subsonic air, and that can pretty accurately represent what Sabre, what the pre-cooler in Sabre would actually see in real life, because it's not going to see any shocks itself, I don't believe. Regarding the Delta Q stuff, I'm not going to try and answer that because I don't really know. So yeah, but that's the shock structure anyway.
Fair enough. That's great. I hope there'll be more kind of knowledge around that once you do the integrated tests.
Oh, absolutely. Yeah, I mean that's yeah. So if I go back to that roadmap, I mean that's learning to get integrated tests. So we go, we've done our heat exchanger on its own, we've done a core on its own, and then we've de-risked a significant amount of it by doing them chunk by chunk like that. But there is definitely still kind of integration parts between the systems that need to be tested. So that's what those are there for. Yeah.
Another anonymous question. Hope that answers your question, Lawrence, by the way. Again, we touched upon this just now, but another amazing presentation, very well broken down. Any advice on recent grads on how to break into the industry, or more specifically, how to get a job at Reaction Engines? I know it's a very competitive grad program. I know we already touched upon this, so maybe give them a couple more tips on how to specifically please the managers at Reaction Engines.
Well, I think so. I'll probably be overlapping a bit with what I said before, but we're all a really enthusiastic bunch, right? And we really we care about this stuff as much as you do, and just showing that, you know, that is enough. And I think, as I kind of said before, or as I alluded to before, being able to kind of recognize your skills as an engineer or a kind of a physicist or whoever, being able to recognize your skills and how you can, and your capabilities, I suppose, and how you see yourself placed in reaction engines. I know for me that I believe that helped. I mean, I haven't talked to my interviewer about it, so it might not have, but from my point of view, being able to actually to picture yourself in the company contributing and being able to kind of define how you could potentially contribute and kind of, you know, be part of what's happening is really good, because it's all very well and good being super enthusiastic about it, but actually being able to kind of say, well, these are the skills I'm really good at. I understand at the moment you are doing X, Y, Z, and this is where I think I could fit into that. I think that's really useful. So I'd say that's kind of the magic bullet, if there is one. But yeah, I think being well-rounded as well as an engineer and a person. People like kind of, you're going to be working with these people and they want to know that you are personable. So, like, personally in my interview, I talked about my hobby of baking bread, and that went down quite well. So, I mean, I don't recommend you take up baking bread in your spare time to get a job at Reaction Engines, but I think actually having a really showing them your personality as a well-rounded individual as well as an engineer is really important. And I think that goes for any job, to be fair.
Yeah, definitely. I hope that answers your question, and to anyone else who's still looking to break into the industry. Another, not a question this time from Oliver, but he's saying thank you for a fantastic presentation, and he's recently started a space-themed YouTube channel, and he's making a series of videos about UK companies in space, and he feels like lots of smaller space companies, and I say small relative to SpaceX and Rocket Lab, and he's saying this presentation will really help his research for his reaction engine video. So good luck, Oliver.
Oh, good. Well, I hope I haven't said anything that's too IP sensitive that I've just given away. But yeah, no, good luck. That sounds really interesting. So
I'm sure you had a disclaimer.
Oh yeah, hold on. Let me just skip to the.
So, yeah.
Just so everybody knows, I don't really know what it says. So yeah. Anyway.
Oliver, this is for you. You need to pause and take a screenshot here.
Oh yeah, I'll keep that.
Awesome. Yeah, I'm glad you enjoyed it, Oliver. Another question from Spiros. I'm not sure if you'll know this. What is the approximate weight of the engine per nacelle?
Oh, you know what? I was actually, the other day I was looking at a math spreadsheet, but I can't remember the numbers off the top of my head. So,
okay.
But I will tell you that it's a big engine. It's much bigger than you could probably picture it being. I think at one point, if you have a look on our, I think it should still be there on our media page on our website. I believe at one point we had like a human to scale next to one of the engines. Yeah. So in terms of size, that should give you a pretty good idea of how big it is and probably how heavy it is as well. But yeah, I don't know a number off the top of my head, unfortunately.
Awesome. There's a couple of questions in that link with each other, so I'm going to merge them. One of them's from Matthew and then the other from an anonymous attendee. Thank you for joining us once again. And the question is, of course, I think you mentioned Reaction Engines has grown to over 200 people now. But which departments within the company would you like to get some experience in during your grad scheme? And where do you see yourself in the future? Because I know you've only been in the industry 10 months. So you might still, of course, be making up your mind and learning every day. But what departments have kind of, I might want to work there?
Yeah, so that's really good. So one of the nice things about working at Reaction Engines is that because it's quite an intimate company, I say small, it's kind of mid-sized, I suppose now. the advantage is that you can get real exposure to like all the departments you want, and they're really keen. The management team are really keen for you to do that as well, because again it makes well-rounded individuals that want to work at the company but want to stay with us. So I mean personally, I've worked on our Demonstrator engine, and I've worked on our motorsport stuff. I imagine I'd want to get some exposure to the hypersonic flight stuff, probably in like an aerodynamics role. That would be quite interesting for me. I did quite a lot of aerodynamics at uni, and specialised in that quite a lot, I suppose. So I think that will probably be the next step for me. My next step actually on the grad scheme, I'm going to go into the control systems department and start looking at control system stuff. So that'll be interesting. Kind of long term, I think I'd probably see myself, probably in an aerodynamics role, but that's not to say I haven't been enjoying design engineering. It's being really interesting and a really useful skill to have as well. As design engineers are always in demand anywhere you go. I imagine I'd probably be looking to go towards kind of, for my next move, towards like the hypersonic stuff in an aerodynamics role. Yeah.
Awesome. I wish you the very best of luck. I hope that answers your question, Matthew.
Thank you.
All right, let's move on to back to a science-y question from Andrew. How does the movement of the intake cone? We're again talking about the intake now.
We love the intake, don't we? Yeah. Wow.
How does the movement of the intake cone affect the shockwave structure? And can this be simulated accurately? Because I know you're not really doing this with the precooler, but can this be simulated accurately, or is that something you leave to full-scale testing?
I think so. I think he's talking about like a dynamic shock structure, if I'm right in it. Yeah. Okay. So yeah, no, you're right. I totally respect that the tests have been static in that regard so far. I believe we have done work into looking at the kind of dynamics of shock structures around nacelles. It's an incredibly complex topic, as you can imagine, and there's a whole host of instabilities that can arise kind of further down the engine because of funny shock effects happening in the nacelle. And I think ramjets and scramjets have similar issues where they're really sensitive to the shockwave structure at the front of the nacelle, and it can completely flare out the engine. In terms of modeling, I guess this physically testing that will have to be a job for the integrated for a flight test, I imagine. But actually modeling that, I'm not 100% sure how much work's been done on modeling that. I imagine it's definitely been considered, for sure. But I imagine Richard Varvel's probably the guy to ask about that and not me.
Awesome. I think another question coming in from Spiros, it might be one for the managers, is do you believe that Skylon will be released at the end?
Yeah, I mean, so I suppose Skylon is what people recognise the most about single stage orbit stuff. Yeah, I think we've recognised that actually limiting ourselves to like a Skylon space plane probably isn't. I mean, first of all, we're a smallish company, and undertaking an engine development project as a smallish company is a big enough feat in itself. And the fact that we're doing that is obviously a huge amount of work. And I think to develop an airframe alongside that, whether it be Skylon or something else, would be almost insane, frankly. I mean, it'd be such a huge amount of work, and it wouldn't do Sabre justice, essentially. So what we've realised is actually that Sabre's so versatile is that we can apply Sabre not just to single stage and 2-stage to orbit stuff, but we can also start looking at hypersonics and things like that. So we've tried to kind of, in terms of airframes, we tried to kind of broaden our horizons a bit, I suppose, in that respect. And kind of in doing that, redirect for focus onto Sabre, which is the real critical part of this anyway. I mean, Sabre is what makes it happen. So that's the stuff we're concentrating on.
Yeah, that definitely makes sense. And then you can branch out into different, as you said, you've got motorsports, you've got the energy industry,
Oh, exactly. Yeah.
potentially looking at commercial airliners that could, I mean, there will be technology which will change them eventually. Because I mean, everyone knows they're not very efficient currently.
Yeah, precisely. Yeah, and there's
Yeah.
huge drive in the kind of world as a whole to kind of change the shape of the aerospace industry as a whole. And I think we fit quite nicely into that.
Definitely, yeah.
Yeah.
Cool. I hope that answers your question, Andrew. And Oliver said he took the screenshot. Well done. Cheeky question from him. He says, if his channel takes off, pun intended, what are the chances of attending and filming a launch? So I think that's a question for me. Oliver, we'd love to have you on Space Tour Live. We are all about trying to expand the reach of the space industry. So I think my technical team will get in touch with you and we'll try and arrange something. Matthew, thank you for answering my previous question. And there's a question for you, Jamie. Will there be a growing demand for aerodynamic/thermal engineers with hypersonic knowledge experience in the future?
Yeah, reaction engines. Does he mean in general or reaction engines specifically? Or
I think he's alluded to reaction engines, but I guess
the answer is the same for both, I suppose. I mean, there's definitely going to be a growing demand. I think like reaction engines is growing as a company all the time, so we've got demand for pretty much everything. I think not that long ago we actually advertised for a PhD in our hypersonic testbed stuff. Yeah, I don't know if it's still open. I think it's closed now, but there are like absolutely like opportunities for hypersonic aerodynamicists to get in on the action. And hypersonics, as we kind of mentioned before, is like such a growing industry again. I suppose it kind of went through a bit of a lull at one point, but it's on the up again now. And like governments and companies are equally all really interested in it. So yeah, it's definitely a kind of growing field that people can fit into for sure.
Another question from Alex. I think we're getting to the end of our questions now. Alex is asking, is it helium that flows through the precooler as a coolant? And is the precooler coolant in a closed loop, or is the spent coolant expelled?
Yeah, really good question. So yeah, it is. It's helium flowing through a precooler. And I think it actually does say here, oh no, it doesn't. It said there was some slide, I think it was in a small print. Yeah, it's in a closed loop for helium. So essentially we've got, we essentially got an open loop of hydrogen and a closed loop of helium. And that helium is what is our working fluid, kind of, dragging the heat out of the air and putting it into our turbo machinery and our hydrogen fuel, which then gets burnt off. But the helium, it's a closed loop.
Awesome. I hope that answers your question, Alex. Thank you so much for joining us. And I think that brings us to the end of our questions.
Wow.
But yeah, it's been so great talking to you. Thank you so much for your time.
Oh, no, fantastic. It's been absolutely brilliant. Thanks for having me here. I really enjoyed it, and the questions were brilliant. So yeah, thanks for all the questions, guys.
They were, yeah.
Yeah, I know. I'm really glad that everybody enjoyed it. Keep interested in space. I suppose it's everything's kicking off, I suppose, at the moment, and it's getting really interesting. So yeah.
Awesome. Yeah, thank you so much for joining us, and thank you so much to all of you who joined us tonight, whether you were on Zoom or YouTube. If you're on YouTube, please remember to like, share, and subscribe if you enjoyed tonight. And remember, you can catch up with all of our previous Thursday night talks on our YouTube channel. So do head there and check those out. We're going to be back next Thursday with another Thursday night talk. But before then, as some of you may know, we have a Tuesday night roundup with Nick Howes and Terry Mosley, who are both extremely experienced astronomers, and they know a whole lot about space. And they'll be giving you a roundup of everything that's been happening in the space industry over the past couple of weeks, all a roundup of what to look out for in space. And please do tune in on our YouTube channel on Tuesday at 7 p.m. and again at 5:30 next Thursday for another incredible talk. Once again, thank you so much, Jamie, for an incredible talk. I hope everyone who's joined in has really enjoyed it. I've certainly learned a lot and refreshed my memory on engines from back at lectures at uni. Yeah, thanks so much.
No, thank you. It's been really enjoyable. Thanks, guys. Thanks, everybody.
Awesome. Also, just another reminder, if you are in driving or walking distance of the Space Store in Didcot, we are now open every day from 11 to 3 p.m. So please do go check us out if you haven't already. We've got the best coffee in Didcot and some great new smoothies. So go check that out. We've also got an in-store quiz for the kids and adults as well. So go check that out at Space Store Didcot in the Orchard Centre. Awesome. Everyone, have a good evening, and we'll see you on Tuesday. Thanks, Jamie.
Thanks, guys. Catch you later.